using non-resonant inelastic X-ray scattering. I first of all would like to thank my collaborators. First of all, my PhD student Martin Sundermann. It's to a large extent his PhD work here I'm showing. Maurits from the Max Planck, the whole group from the Max Planck Institute. Maurits provided the analysis code Quanti, Stefan will help us with the experiment, and many discussions with Peter Thalmeier and Howard Cheng. Marco and Ali from ESRF and Grenoble helping us at the beamline, and we got the samples, single crystals from Mark Morgen's group at the University in Amsterdam. And Martin and I from the Deutsche Forschungsgemeinschaft. So uranium with helium to silicon too. We heard quite a bit about it today, so that I'll only recap quickly some properties. Interesting is the hidden order state and how can the hidden order form. The hidden order occurs at about 17.5 Kelvin, which is shown here in the resistivity versus temperature diagram. Here you see the kink where the hidden order occurs. There is a superconducting transition at lower temperatures, which we are not going into today. It should be mentioned that there was a very small magnetic moment had been observed actually in the hidden order phase, but it was then attributed to parasitic minority phase. So it's not something like an antiferromagnetic phase with a very small moment. Interesting is that the hidden order phase is very close to a large magnetic moment, antiferromagnetic phase, by simply applying a little bit of pressure. I'm showing here the temperature pressure phase diagram, and only a few kilobar and the hidden order actually disappears and you are in an antiferromagnetic phase with roughly the same transition temperature. Known about the hidden order phases is that it's a second order phase transition into the electronically ordered state. It goes along with a large loss of entropy, about 0.2 and 2. There's a perfect surface reconstruction. It's also known, I think it's from the Hausmann-Altman experiments of Hassinger et al., that the thermic surfaces of the hidden order and antiferromagnetic phase are very similar. And it goes along with a loss of fourfold symmetry. These are magnetic torque measurements and high resolution diffraction, where actually we're lowering down into the into the hidden order phase. There's a splitting of diffraction peak. However, I learned now that is still a matter of debate because this apparently has not been repeated by another group yet. So let me see whether this is really valid. There are energy scales. There's the hybridization gap of about 13 millivolt as observed in STM, which opens up a bit above the hidden order temperature. There is a hidden order gap of 4 millivolt, which has been observed with the charge and also spin channel I mean scattering. And then there is a resonance of about 1.6 millivolt observed in the charge channel by Raman. We have heard about this, and in neutron scattering. I think there is general consensus that if we get closer in understanding what ground state symmetry we have, that this should bring us closer to understanding actually the symmetry of the hidden order parameter. And that is where we now step in with our work. I'm showing you here the magnetic susceptibility versus temperature, which has a huge anisotropy, which is reminiscent of crystal field effects. You may wonder now why I'm simply measuring it with inelastic neutron scattering, but as in many very delocalized materials, also ceriums, it's very difficult to measure actually crystal field excitations, and certainly metallic uraniums, it's next to impossible. I think there are only very few localized uranium compounds. Uranium palladium 3 is one example where crystal field excitations actually have been observed with neutron scattering. Another complication is, of course, actually what configuration are we starting with, the F2 or the F3 configuration. I mean, we heard here too, there are very recent data by Booth et al. LH absorption data, and they find a valence very close to 3. Then from your data, I mean, you can describe your line shape with an F2 configuration, right? And here also, I think the high temperature susceptibility is more like an F2. I don't think it's either or. It is more the question, what model do we start with to describe the symmetry? And there, So as a result, of course, there are many different crystal field models and also symmetries, suggestions based on these different models. So that's where we come now in, and we say, well, we try to find out from which crystal field wave function actually this in order or itinerant state might build up. And I think that starting from an F2 is a good ansatz, and we will see from our data that it's indeed a justified ansatz to start from here. And if I assume an F2 configuration, I have the J equal 4, that means it's 9-fold degenerate. And in the tetragonal symmetry, this 9-fold degenerate manifold splits up into 7 states. 5 singlets, 2 doublets. Written here in the JZ representation, I have 2 gamma 1 singlets. They're the mixture of JZ0, JZ4. They're here distinguished only each other by the sign, which means they're rotated by 45 degrees. Same for these 2 doublets. It's a plus minus 1, JZ, plus minus 1, 3, and they distinguish each other by the sign, they're rotated by 45 degrees. So that is now the big question, which one is the ground state, and that's what we want to do. But let me flash, there are really many theories, many suggestions, all assuming different ground state and building up a theory on top, and I hope by maybe sorting out a few, or we can get closer to understand what the even order is. So our method of choice is non-resonant inelastic X-ray scattering, we call it NICS. We do this with hard X-rays, and we do it at the OH, which is transition from the 5D to the 5F, for probing the 5F symmetry. It's a photon in, photon out method. We do this with hard X-rays. Hard X-rays means we are really Bond sensitive. Yeah, surface is no issue for us. The other nice thing using high energies is that we can reach very large momentum transfers. So if you go here to high scattering angles, we have actually very large momentum transfers. And that means if I expand here my transition operator, I cannot truncate this expansion after the first term. So I don't have only dipole, I have higher multipole contributions to my scattering signal. And this is I'm showing here. If I actually do make this expansion, I can factorize it in the radial and an energy-dependent part. Here's the radial part versus the momentum transfer shown for dipole and higher multipoles. And you see the dipole is of course very large, very strong, and large, small momentum transfers, whereas the higher multipoles at typical momentum transfers, which we can reach 10 raised to angstroms, is already quite strong. If I look now at the scattering function here versus energy transfers, and I look at the parts here, the dipole, higher K equals 3, K equals 5, I do see that this is here with the dipole, that even new excitations actually come up. This has already actually been measured by Q4. He measured the powder sample uranium dioxide. Here, this is the 2.8 reciprocal angstroms. This one here. This is dipole. Yeah, you see this dipole shape here. There is here it is actually rather funnel-like shape. This is not in these calculations because we use the same line width for all the multiplet excitations in our calculation. Whereas when you go to large momentum transfers, like here, you really have these very sharp excitations coming up, and these are the only dipole excitations we call it. And this I just would like to show. This is what Andy has been showing yesterday. He did X-ray absorption, and has been cut off. He did X-ray absorption on the uranium into silicon at the OH, and he really measured here in the dipole regime. Yeah. Whereas we now want to concentrate here on large momentum transfers. So we also measure at the OH, but at higher Q. This is, I think, the difference. And when we do such an experiment now on a single crystal, vector Q parallel, let's say C, and in the plane parallel 100, then we can do the same as in an X-ray absorption experiment with linear polarized light. And we have, well, that is just flashing the beamline where we did it in IP20 and ESRF. We come in here with photons, we scatter, we do backscattering to have high momentum transfers, and this is our final energy, so 6.5 kV, our resolution, and these are the momentum transfers we are working with. We could realizing that experiment. So this is what we measured. Above the hidden order transition, we measured parallel C, parallel 100, all momentum transfers, but we do see actually a large dichroism. Now we have to analyze this data, and the analysis we actually do with a multiplet code. This is the multiplet code quantity written by Maurits Haverkort. We start with the atomic values which we extract from the Cohen code, and then we have to adapt a few parameters, like we do take along here that we not only have L, S, J, J, Z as quantum numbers, X and string orbitals allow some mixture of L equals 3, 4, and 5. We adjust reduction factors to take screening effects along in the solid. We have 5F about 50%. And we have some line widths, Gaussian for resolution, some for lifetime effects, and some Mahan to mimic sort of the attenuancy. And we adjust this actually on the isotropic spectrum. The isotropic spectrum we measure by measuring many, many directions in the crystal. Because we are beyond dipole, it's not enough to measure 3 directions, we have to measure many. But then Maurits Haverkort gave us specific instructions what to measure, so this is the measured isotropic spectrum. And in the simulation, we simply sum up over all crystal field states. And then by doing this adjustments, we actually get a pretty good description of the line chain, which we think that this is a rather good justification by starting with an F2 configuration. We have done now the same simulation for all crystal field states here, gamma 1 to gamma 5. And we compare this now, so this here corresponds now to these crystal field states. What I'm showing you here is always when you have the biggest contrast. So I have the gamma 1 theta 90 degrees. That means I have a pure JZ form. Yeah, that's what I'm showing you here. Of course, I can mix in the JZ0, then I basically go from here to here. This would be then the gamma 1 to 90 degree, where I only have the JZ0. Yeah? So it's a front 2, the only difference is a slight adjustment because I will twist the orbital because of the side 2. And the same here is for the gamma 5, where I show you the biggest contrast is here for the gamma 5 plus minus 3. If I would mix in some of the JZ1, I would go via 0 to this type of patterns. And now we compare this with our spectrum. This is the measured spectrum I showed you before. This is the simulation. And I think if I compare simply red over blue, and I compare it with this, I can eliminate at once many, many spectra. I have only 3 left. The gamma 1, 90 degrees, the gamma 2, the gamma 5. In this extreme case where I have almost a plus minus 3 without any 0 mixed in. So to be more quantitative, because this is a nice thing that you actually can do quantitative simulation here. I compare the dichroism of these 3 states here with a measured dichroism. The black dots are the measured dichroism and the lines are the simulation. So I have a measured dichroism of 35%. The percentage we construct basically is from minimum to top to a certain peak ratio in the isotopic spectrum. That's why we give it percent. So the measured one is 35%, and it is clear that the gamma 5 gives, although this is the best case, gives a dichroism which is far too small. So then you also have to eliminate the gamma 5 as the ground state. And they're left with these 2 states. But also here we have to say the gamma 2, well, the simulation gives us the dichroism which is somewhat larger than the measured one. In the gamma 1, we can mix in, of course, some of the JZ0. We could make the dichroism somewhat smaller. I would like to leave it like this. For the time being, I can say we do not observe the maximum possible dichroism. We have a big dichroism, well described with the gamma 1, relatively well described with the gamma 2, but there is maybe some dichroism. It would have been bigger than what we actually observed. So far about 25 Kelvin. Now we did the temperature run that we warmed up to 300 Kelvin. I mean, that's what you do in spectroscopy. You want to occupy excited states, but we basically see nothing. We see no change within our statistic, reliability, no T dependence. And from this absence of T-dependence, we still learn something. We can say, well, the states with very little dichroism must be above 150 Kelvin. Otherwise, we would see it in our T-dependence. The states with stronger dichroism, they must be even higher. Otherwise, we would see it in our spectrum in this temperature interval. So this type of spectroscopy actually we can do. So now we look at the hidden order state. We cool down to 5 Kelvin, and again we have to say there is no change across the hidden order. And this, I think, agrees also with what you didn't see. Also in your data, you did not see any change in the dichroism when you cooled it into the water phase. So these data are actually quite consistent. So far are our experimental results, and now of course we try to put this in perspective a little bit with what other people have done. And I have to say the good and bad news. The good news is that what we find when the gamma 1 and gamma 2 are actually dominating the ground state is the TMFT calculations from Halle and Kottlia have found. So this is quite reassuring. However, the bad news is that apparently if you have a single ground state, there is a problem getting enough entropy. And this entropy of 0.2 and 2 has been observed or cannot be ignored. So it would be wishful that there is some other state present, possibly, ideally, the gamma 5 doublet. Here, I've darkened this now. We had this, or we discussed this, that one also would need the gamma 5 doublet state if one wants to construct the rank 5 hidden order parameter, which then would give actually or produce this loss of rotational symmetry. However, this is something I cannot discuss because I do not know how valid this observation is. I think that has to be seen in the future, whether this can be reproduced or not reproduced by another group, this observation. And then we have to say, let me go back here. I said we did not observe the maximum possible dichroism from the simulation. That means that there could possibly another state contributing to the ground state, so that our ground state is sort of a state of a mixture of quantum states, if you like. But that cannot be by Boltzmann occupation, because I did show you from the absence of T-dependence, the next higher state must be at least 150 Kelvin above the ground state. So what one could imagine is that we maybe have inter-site processes which mix in another state, or converse type scenario, and this is what I would like to show you. Well, I mean, it's a very simple picture which we are having here. I've been thinking about setting up the energy level diagram for uranium to silicon 2. And what we do here is actually start with a Kramers doublet, with an F3. And we're wondering, how can this F3 doublet, Kramers doublet, now hybridize? Well, it will of course hybridize with the manifold of the F2 plus the extra reduction. I'm trying to have the number count right. We have here the gamma 1, the gamma 2 are possibly either one of the two or both low-lying states. They can be close in energy that we cannot distinguish from our data. But they will always also hybridize with whatever other states are 150 Kelvin higher in energy, possibly a gamma 5 or other states. Yeah? So that we then end up with a ground state. We know there is a hybridization gap of the order of 150 Kelvin, which is rather large, 30 millivolts, so it's absolutely comparable. And in this ground state, we then would have a contribution, we would have a mixture of all these states. So it means we have a ground state, which mainly, of course, consists of these two singlets, but contributions from higher states are absolutely possible due to this hybridization of the F3 with the manifold of the F2 configuration. And with this, actually, I'm already coming to the end. I'm coming to the conclusion. We have done a non-resonant X-ray experiment. I should mention, we have seen so much Raman. Many people actually also call it hard X-ray Raman, this method. On uranium with silicon 2, we do observe a strong dichroism. We can describe the line shape very well with an F2 atomic approach, which does not exclude, there is no statement behind that the material is not itinerant. It's of course itinerant, but the symmetry seems to be determined by the F2. We do find that the ground state symmetry is majority singlet gamma 1, 90 degrees gamma 2, which means it's majority adjacent plus minus 4. This agrees actually rather well with Fitzgerald's static susceptibility very early on, which Niemeyer's did in 87. It also agrees with the description of elastic constants and with the CMFT calculations. We did not observe any T dependence up to 300 Kelvin, which puts constraints onto the excited states. We don't see any change across the hidden order transition. And in order to build up the hidden order state with singlets, which might be difficult, our new data do allow the possibility to build up the hidden order state from a ground state, which is the composition of quantum states. And with this, I would like to thank you for your attention.
Okay, so based on just your data, without bringing in additional analysis, which is neither based on your data nor based on detailed calculation, is this, which says that the ground state definitely contains 4 or minus 4 of F2. Right?
Correct.
Okay. Yeah. So this statement is entirely consistent with Cowler-Porter, and it's entirely consistent with what Sean presented from the other. Now, the entropy argument that you are bringing up is not based on any calculation. So the proposal that was done in Sean's paper is that what happens there is a density wave. So density wave opens up a gap. I think there's an agreement across the board that the Fermi surface reconstructs, 40% of goes away, and that's where the entropy is lost. So the entropy is lost due to the gap. Gap opens up because there is a spontaneous symmetry broken, second order phase notation. What breaks the symmetry, I think we identified it in our study, so it's really the mixing of this gamma 1 and gamma 2, which didn't happen above the transition, happens below transition, that opens up the possibility. That's the driving force. Basically, it wants to be lower than, gamma 2 wants to be lower than gamma 1, and isn't D for H, it's forbidden. So this is entirely consistent with that. And then the last argument is the Boltzmann population. So if you would consult with EMFT people, they will say that in strongly correlated system, all states are partially occupied always. So you, by doing the Boltzmann probing, you are not really doing this the same way as uncorrelated. It's more complex, and therefore you can get more anisotropy from other states being involved somehow in this transition. This scheme is not. This scheme maybe doesn't contradict anything, but it doesn't also. It's not based on it.
This is absolutely right. But what this actually shows, what we do get from our data is the base excited state has to be higher, it cannot be low.
Yeah,
because I've done enough Richard sketching on correlated systems, and you do see the occupation of other states.
This is consistent with again calculation. The Pauli Complex paper calculates that also being above the same number.
What this actually basically is a cartoon showing how. If you need, for building up your hidden order state, if you do need the symmetry of some other state, like a duplex state, for example, then this is absolutely possible in the case of strong hybridization. If you start from the S3, which hybridizes from the many
other things are possible.
That's all, it doesn't say anymore.
Yeah, that's right. So the only other thing from spectroscopy we can say that we do not see the transition from ground state into that gamma 5, which means that that transition is beyond the gap, so which is about 6 millivolt, you quoted 5, maybe between 4, between 4 and 6. So this is more than 6, so we can't see it. It just doesn't, there's no resonance there, it's elapsed. It's all mixed up over there.
Yeah, I agree.
So the only resonance is these two lower
I can
states.
only say it is here or higher.
Yeah.
I'm not saying it's
Yeah.
there.
So the only close being state are these gamma 1, gamma 2.
Only these
Uh,
two or one of them.
Right. They actually don't exist. They are too broad to be seen in the normal state, the paramagnetic state. When gap opens up, we see that as a resonance. Before the gap opens up, we see just a broad.
Yeah, I know that reason. Yes.
To-
But may I ask the question, why does neutral sketching see anything then? Do you say the resonance you're seeing is 1.6 millivolt is the transition between the gamma 1 and the gamma 2?
Yeah, and this is exactly what Newton scattering sees, that the collective mode, dispersive collective mode, is exactly the same.
If I can comment on this, in the Ritz measurements, we saw that the matrix element that should have been giving us transitions into crystal field modes, if there were simple crystal field modes, it was giving us very, very broad, something that looked like a band excitation continuum stretched over 300 MeV or so. And that's, I guess, in your measurements as well, you see something sort of continuum-like or something like that. So this is specifically with reference to the models in which one is framing everything in terms of a crystal field, in terms of crystal field states. And if one wants to frame it, wants to think of it in terms of continuum states, one needs to add more nuance maybe, but as a contextual comment, this is is that maybe the way it should be framed with respect to the higher energy state? Or
Newton scattering sees this mode as dispersive mode, not just a flat mode. So that means that you can't really read it as entirely local.
yeah.
So
As a cone. This is a diagram of the ground state. Yeah? So if you warm up, you have to look for another piece of the Hilbert space, not necessarily only this one. You can look, for example, for the gamma 1 singlet that's decoupled from the F3 that also exists in a different Hilbert space. The gamma 5 duplet also exists. So all those you will see if you occupy state by temperature. But if you're low temperature, you start with the green ground state, and you will see all excited states. And this ground state has this multi-component character. Depends what you believe is in it, but the experiments tells you that this is possible. Right? So this is what you see. And the experiment tells you actually pretty good that the F2 ansatz, as far as spectroscopy is concerned, is quite good. And it has to do with the so-called interference and effect that you have F2 and F3 mixtures, you still pick up the F2 symmetry quite well. And that's why this technique is for that purpose, of finding symmetries so powerful.
and it says even more, as I understand, it says that it's 4 and minus 4 are the main contributions.
Yes. Correct.
Right?
And
So
you
it's
can
not
say that.
1, 2, 3, and etc.
No.
That excludes the gamma 5 itself.
Well, it
No,
doesn't
that's
exclude
what-
gamma
well,
5
it's
from the
correct.
mixture. And it also, itinerancy will directly correct it, will directly change this to some extent.
Certainly, the majority is dominated by these two states, but this may well split into a ground state.
We cannot exclude it.
This is a mixture.
You have no evidence that it plays an important role, and
No,
and
but
again,
no. Instead, it's only the possibility exists.
yeah, but there is also the argument if you take back and say that it's all F2 or majority of F2, then we have symmetry argument that gamma 5 doesn't mix to gamma 1. So they don't.
No, we don't. No. Then you misunderstood. You do not need to be in the same representation here to mix this.
Well, if you do hybridization, then
it's
of
for
course.
hybridization. Yeah. It is not that I.
But now you
mix
argue that
just the same.
hybridization is high, it's strong given at room temperature because you didn't see any temperature dependence. You didn't see temperature dependence, and then you will have to say that hybridization is really temperature independent parameter.
Well, if you're thermally populating a continuum that stretches up to 300 MeV, if there are continuum states, then the
But at
the
5K
thermal
is the same.
properties
So.
may be.
I like to say about that, maybe we can.
Yes. Maybe we can have a more detailed discussion.
Are
Are there any last questions from outside of this cross section, which includes me?
Yeah, I could have a much more naive question. Yeah. So sorry, you probably explained, but I didn't catch. I still don't understand. So why did you go see a little bit different symmetry for the ground state?
I think the reason is that we are truly bulk, and as Annie pointed out yesterday, he does a really surface sensitive experiment. Yeah. So I think if you do a surface sensitive experiment, in many ways, maybe you may lose some dichroism, because I think you even gamma 5 to gamma 1, you even allowed that, I think yesterday. And we see the strong dichroism. It's very hard to produce strong dichroism, and this is clearly a bulk effect.
I would comment the matrix elements are different, and we don't really know what's going to come when itinerancy is factored in. It does seem like what they're showing is supporting that there's more of a role for MJ equals 4 states, which are specifically gamma 1 and gamma 2 associated symmetries. Now, as soon as electrons hop from one site to another, the hopping matrix element is going to keep spin but not keep the local orbital symmetry, and you'll get...
You simply did here the calculations, the X-ray absorption calculation. If you do it for the gamma 5, so you see, this is the dichroism which you calculated for the X-ray absorption. This is what you observed. You have enlarged it. You have about something like 10.5%, you see.
Yeah.
You calculate something like 40%, and therefore you are also corresponding to gamma 5 if I have been you. But if you calculate the X-ray absorption, you clearly see more. For the gamma 2, the gamma 1. So I think, you can discuss that.
Right, well-
You cleave AA, not AC, and I think there are many ways in the surface experiments.
Right, no, I'm only talking about itinerancy. I'm not
Yeah.
talking about the
Okay.
interpretation with respect to a single site model. But anyway, thank you very much for the question.
Yeah.
All right, let's thank the speaker one more time.